Hello, class. Today we are going to introduce Chapter 9, and we are going to be working on first sequences and series, and then after that, the binomial theorem. And so I am going to start off with a really fun comic called Foxtrot. It has kind of a math humor type bend to it, and so that's why I like it. But we can look at these panes. You have the blonde kid saying 1 cheesy tortilla chip, and then his friend saying 1 cheesy tortilla chip, and then 2 cheesy tortilla chips, and then the friend going 3 cheesy tortilla chips, and then 5 cheesy tortilla chips, 8 cheesy tortilla chips. And then the older brother says, math geeks shouldn't be allowed anywhere near certain foods. And then the blonde kid said, what's wrong with Fibonaccios? And then his friend is saying, uh-oh, there's only 12 left. And just a reminder, this was the Fibonacci sequence joke. 1, 1, 2, 3, 5, 8, and then 13 is supposed to be the next one. And it is generated by adding 1 plus 1 gives us 2, 1 plus 2 gives us 3, 2 plus 3 gives us 5, and so on and so forth. So, Fibonaccios. Super cute, huh? All right, so we are going to spend today as an introduction to the concept of sequences. We're actually doing 9.1a. I'll sneak that little A in there. And this particular topic is going to be focused on what are called discrete relationships. This is a discrete relationship. It is not continuous like the other one. And it is discrete because it says a function whose domain is the set of positive integers. It's a really silly way of just saying each of these numbers in this sequence here is just the counting numbers. So this is saying the first term is 1, the second term is 1/2, the third term in the sequence is 1/3, the fourth term in the sequence is 1/4. So because those numbers 1, 2, 3, 4 are meant to count the number in the sequence, these are always going to be counting numbers. So you have this sequence or pattern of numbers, and the x, what would be the x, which actually is the n in this case because we're talking discrete, the x or the domain value is just the counting numbers. And then the y, which is f of n, is going to be the number in the sequence. So the first number in the sequence is 1. The second number in the sequence is 1/2. The third number in the sequence is 1/3. And the fourth number is 1/4. So the reason the domain is positive integers is because the integers count the number in the sequence. So today will serve as an introduction to sequences, which is basically a pattern of numbers. So here's some thoughts on the notation. N is the number of the term. So if you want the 100th term in the sequence, n would be 100. If you want the 99th number in the sequence, n would be 100. So it is whatever number you are in the sequence. An is what the term is itself. So if I give you a sequence here of odd numbers, and I say if n equals 3, I'm looking for not the first term, not the second term, I'm looking for the third term. So for the third term, n equals 3, and a sub n equals 5. So in just normal person speak, I'm asking you if n equals 3, what is a sub n? You're just looking for the question, what is the third term? And you can write this for n equals 3, a sub n equals 5, or you could just say a sub 3 equals 5. So the normal way of saying this would be the third term is 5. Okay? And we can see that from the sequence: first term, second term, third term, fourth term, fifth term. The third term is 5, but mathematically, this is how we state it. So that's a note on the notation. So if you're asked to write down the first 6 terms of the sequence and graph it, let's just follow the formula to figure that out. So for n, I can solve for a sub n just using substitution. So n equals 1 has me finding my first term. So that would be -1 to the first times 1 squared over 2 to the first. So what I did was substitute in for n equals 1, 1 here, and a 1 here. So what I get is -1/2. So the first term is -1/2. If I substitute in to find my second term, I will plug in 2 for n. So you get -1 squared times 2 squared over 2 squared, plugging in 2 for n. So here I just get 1. That was kind of weird. Everything canceled. If we look at n equals 3, you're finding the third term of the sequence. So that is -1 cubed times 3 squared over 2 to the third. So what we get here is -9/8. Keep going. For n equals 4, -1 to the 4th power times 4 squared over 2 to the 4th. Well, holy guacamole here. 2 to the 4th and 4 squared is the same number. They're both 16. It's kind of a fun little thing with 4s and 2s. So all I get here is 1. Okay. I'm going to continue over here. So continuing, if n equals 5, I get -25/32. And n equals 6, we're flipping back to positive. So these negative powers, -1 to a power, flips off being negative and being positive. So it just keeps switching off. Negative, positive, negative, positive. If the power of -1 is odd, you get a negative number. If the power of -1 is even, like in number 2 and number 4, you get a positive number. All right, back to our problem. It'd be -1 to the 6th. That's just 1. 6 squared over 2 to the 6th power. That's going to be 64. If we want to reduce, we can. 18, 30, we can divide by 4. 9/16. So now I'm going to graph each of these. Maybe I'll use red so it shows up nice. So for n equals 1, a sub n, which we're going to graph on the vertical axis, is -1/2. And then 2 comma 1, 3 comma -9/8, 4 comma 1, 5 comma -25/32. We'll just call it right here. And then 6 comma 9/16. That's very close to 1/2. So again, this is a discrete graph. I am not connecting the dots. If I were to connect the dots, that would mean I'd have a 1 1/2 term, or I could have a 0.6 term. That doesn't make sense. You have a first term, second term, third, fourth, fifth, sixth. So you don't connect because it is a discrete relationship where the domain are only counting numbers because it's the first, second, third, fourth, fifth, sixth term, and we could keep going. So now we're going to be determining the sequence from a pattern. So what I am going to be doing is developing, here, I'm just going to block this stuff out so I have a little more room, is trying to determine a pattern and write an equation that helps me to determine this pattern. So the way I do this is I am going to develop a little table that has me graph n and then a sub n for each sequence. So for the first one, I'm going to draw a little line. Let me do it a little less thick. And say this is for an n value, and this is going to be a sub n. So an n value of 1, I get e. N value of 2, e squared over 2. N value of 3, e squared over 3, and so on and so forth. So the n value tells you the term number, and the a sub n tells you the term. So we can determine the sequence, we can see it, but I'd like to write an equation. So for a sub n, you have an e in all of them, so you know it's going to be e. And notice whatever n is not only a power, but it's also the bottom of that fraction. It's the denominator. So looking at the pattern for e equals 1, we could even do this. We could say, oh, this is e to the 1 over 1. So I can say it's e to the n over n, e to the n over n, e to the n over n. So when we write that equation, it's going to be a sub n equals e to the n over n. So that equation determines the pattern. For B, I'm going to modify by saying, okay, what term number am I? And this is the term itself, a sub n. So I'm going to develop a little table, so hopefully I can see the pattern. So for n equals 1, I get 1. For n equals 2, I get 1/3. N equals 3, I get 1/9. N equals 4, I get 1/27. One thing I notice about all of these is I'm going to write this as 1 over 3 to the 0, just so I can see that pattern. Let me write the 0 a little clearer. This is 1 over 3 to the 0. This is 1 over 3 to the first. This is 1 over 3 squared and 1 over 3 cubed. So once I notice that all of these are powers of 3, so I have all of these 1 over 3 to some power, I then have to notice their relationship to n. So the 1 is all the same. So when I consider the nth term, it's going to be 1 over something, right? 1 over. And then we all know they have 3's in them. You have 3 to the 0, 3 to the 1, 3 to the 2, 3 to the 3. And then we might hopefully notice that whatever n is, this is 1 less than that. Whatever n is, this is 1 less than that. So it's 1 over 3 to the n minus 1. That is going to be our power that we need to generate this pattern. So a sub n equals 1 over 3 to the n minus 1 would be one version of an equation that would generate this pattern. So let's do some more. This next one, again, just to make my life easier, I'm going to make a little table out of it. And again, what we're doing is writing the equation that has this as its sequence. So I'm going to write n and a sub n. So this is the first term, second term, third term, fourth term. So when I look at this, 1 is 1, 2 is 3, 3 is 5, 4 is 7. If I go 5, it's 9. If I go 6, it's 11. And one thing I notice is that if I double each of these terms, and subtract 1, I get the number. So if I double 2 and subtract 1, I get 3. If I double 3 and subtract 1, I get 5. 4 times 2 minus 1 is 7. 5 times 2 minus 1 is 9. So our n is going to be 2n minus 1. So our formula for a sub n is 2n minus 1. Okay. So I just noticed that, like, and does that work for 1? If I do 2 times 1 minus 1, oh yeah, I get 1. But all of these are just 1 less than double the number. So I kind of just noticed that pattern. For this one, n a sub n, I noticed all of the terms in my sequence are perfect squares. Okay, 4, 9, 16, 25, those are perfect squares. And all they're doing is squaring the n. So for this one, it's n squared. So your term is calculated by squaring whatever term number you're on. If you're on the 10th term, it would be 100. Okay, so some of these patterns utilize the factorial symbol. So the factorial symbol we have seen in prior problems of the week. What it is repeated multiplication of numbers that are 2 or greater. But they did have to define for you 0 factorial. I know it doesn't make sense, but it is 1. If 0 factorial wasn't 1, it would break a whole bunch of formulas we're going to learn moving forward. So 0 factorial has to be 1. 1 factorial is 1, which I think makes sense. And then if you go beyond 0 and 1 with our positive whole numbers, what we can understand is that, for example, 4 factorial is 4 times 3 times 2 times 1. It is repeated multiplication of all the numbers from that number down to 1, all the counting numbers. So 4 factorial is just 24. And we can consider 10 factorial, 1 times 2, or we could go top to bottom, doesn't matter. Something cool with factorials is if you do, like, let's say, let's use 10 factorial. If you do 10 factorial over 9 factorial, we don't have to actually calculate what that is. Like, our calculator has a factorial button. It's under math and then probability. And then I believe one of the first ones is the factorial button. But the numbers get really big really quickly, as can happen with multiplication. But if we consider 10 factorial is just 10 times 9 times 8 times 7, and so on. I'm just going to write that out. And then 9 factorial is just 9 times 8 times 7 times 6 times 5, 4, 3, 2, 1. We can consider the fact that like factors in the numerator and in the denominator of any given fraction, they cancel. So look at this. That's like dominoes falling. So 10 factorial over 9 factorial is just 10. So you can consider the cancellation, because a lot of times if it's a bigger factorial, if you put it in the calculator, it's like too big. Like, it just gets too large, and then they either use scientific notation, or sometimes it even says overflow, like it's too big. Okay. So there are 2 ways to define a sequence. The first way is called explicitly. If you have an explicitly defined sequence, that means you can jump to any term. The explicitly defined sequence is also called the nth term formula, and it's given by a to the n equals. And in here, it's going to have an n in the formula. So a sub n, you're going to have an n in the formula, and you can jump to any term. So like the 100th term, the 1000th term, you don't have to know all the terms before that. If you have a recursive definition, this term, which is called the prior term, will always be in the formula. So it's still given by a sub n, but it would be something like 6 plus a sub n minus 1. It's always going to involve the prior term. So if you wanted to find the 100th term, let's say, it'd be 6 plus a sub 99, you would need to know the prior term. So it doesn't allow you to skip around in a sequence. You essentially just have to calculate it all one by one. So if I gave you this sequence, I'd have to tell you, let's say the first term is, for example, 7. And then to generate terms of the sequence, to find A2, I would say, okay, A2 equals 6 plus A1. So that's going to be 6 plus 7, which is 13. Okay, so it uses the prior term in the formula. And then if you want to find A3, A3 is 6 plus A2. Because when it says a sub n minus 1, it means the prior term. N is 3, 3 minus 1 is 2. So what that means is you need to know the prior term to find the next term. So it's 6 plus 13, that's going to be 19 for a sub 3. And I'll just do one more. For a sub 4, looking at the formula at the top, which is right here, it is 6 plus the prior term, a sub n minus 1. That's a sub 3. So 6 plus, got to plug this in, 19 is going to be 25. And so if I were to need the 100th term, I need to go up to 100. So recursive tells you what's happening. Like if I look at this term, it's basically saying, hey, you add 6 to advance the sequence. So if I look at this, it's plus 6, and then the next one would just be plus 6. So if you're able to read it as it's intended, it's just saying take 6 and add it to the prior term, and that's how you advance the sequence. Oh, and we add 6 again right here from the beginning. But to generate the terms, it is harder. You can't skip around. You have to go in order. 7 plus 6 is 13, plus 6 is 19, plus 6. And we're going to learn how to write these equations for sequences that are like more basic, like adding by a consistent number or subtracting or multiplying or dividing. We'll learn how to write those explicit formulas, but we need to know how to write both the explicit and the recursive formula. So that's what the difference between those are. So for example, write the terms of a recursively defined sequence. And in this, they have to give you the first term. The first term is A1. And then they have to give you a formula for advancing the sequence. Because I like tables, I'm going to create a little table. So for n equals 1, it tells you that a sub n is 5. So this is saying the first term is 5. This information is given to you right here. So the first term is 5. Then to do the second term, you are finding A2. And what I'm going to do is look at this formula to find A2. So A2 equals n. In this case, n is 2 plus 4 times A1. Well, A1 is 5. So A2 is 2 plus 4 times 5. That's going to be 22. So we have the first term, the second term. And again, I'm using the prior term, and that's what the whole thing about recursion is. You have to use the prior term. So for n equals 3, that's our third term. A3 equals n, which is 3, plus 4 times the prior term. A sub n minus 1, that's A2. So A2 is right here. So it's 3 plus 4 times 22. That's going to be 91. Then, fourth term, A sub 4 is n, which is 4, plus 4 times my prior term, A sub n minus 1. A sub 4 minus 1 is A sub 3, which we know is 91. So it is 4 plus 4 times 91. And I get 368. And then last one, the fifth term, A sub 5 is 5 plus 4 times A4. I'm going to use a calculator for this one. 5 plus 4 times 368, and I get 1477. So this is a recursive term. The thing that makes it recursive is this. It uses a prior term. Now, if you want to write the recursive definition of the Fibonacci sequence, this one has to be recursive. I believe it has an explicit formula, but I think it's really complicated. So recursively, we basically want to describe to the mathematician that you add the two prior terms. So the first term is A1, the second term is A2. But A1 and A2, we have to see what those are. The reason we have to say what those are, you need to know the first two terms, because to find the third term, you add the first and the second. To find the fourth term, A sub 4, you add the two prior terms. That's A2 plus A3. To find the fifth term, you add the two prior. That's A3 and A4. So hopefully we can see the pattern to find the A sub nth term. I'm going to go over here. A sub n equals the two prior terms. The first prior term we can write as an minus 1. And then the second prior term we can write is A sub n minus 2. So this says, basically, to find my nth term, I add the one before it and the one before that. And that's it. That's the recursive definition. It's saying you have to go two back. You go to the prior one and the prior one. The one prior to that. Prior. If you need to say that twice. Here is the assignment. We're going to practice sequences, and then tomorrow we're going to get into more specific sequences that allow us to write explicit formulas for very specific types of sequences. Thank you.